Okay, I'm going to solve this friction worksheet in a few different videos probably because I'll do it in a couple so you can focus on the ones that you need help with. I have a box that's sitting on an incline. I'm going to draw the incline in the opposite direction just so I can give you another perspective. Sitting at rest, force of gravity acts on the center of mass. Force normal acts perpendicular to the surface. And if it's trying to slide down, wants to slide down, we know that force of friction has to be acting upwards, static friction, because it's parallel to the surface and it opposes motion. So that's what's actually holding it there. So let's draw an official free body diagram. So A is my official free body diagram. Now all I'm going to do, you don't have to do this. Let me rephrase that. You definitely need to pick an X and Y axis that's conducive to solving the problem. And we're going to pick the X axis down the inclined plane. So this is my X axis. And this will become my Y axis. Okay. So there's my X and Y axis. So you could leave the direction of those forces at some angle like that. So this is perfectly okay. But personally, slant it so that you can see your X and Y. So turn your paper. Okay, there's your official free body diagram. Okay, now I'm going to take one that's not my official free body diagram off to the right. Force of static friction. What's the problem here? Work. There we go. Okay, and I'm going to draw in the components. Now, we have to know there's the angle that they told me. This is alpha, and this angle right here is theta again. So we're going to break this force of gravity up into its two components. So I'm now breaking this up into F, G, and here's theta, and that's adjacent. So that's cosine of the angle. And then here is the X component of force of gravity, and that's going to be F, G, and that's the opposite of that angle. So that's the sine. If you're struggling with that, you need to come see me, and we're going to work on making sure you see it geometrically, okay? So there's my components, because we're going to need it. B, calculate the frictional force holding the box in place, okay? Well, let's look over here. These are the two forces that are in the X direction. And if the box is sitting at rest, then the acceleration is 0 because the velocity is constant and 0. So I'm going to sum the forces in the X direction, which will equal to the mass times the acceleration in the X direction. And we know that that is 0. Okay. And so that is going to be equal to, I'm going to call the force of static friction as my positive force because it's pointing to the right, minus Fg sine theta. And so I can set, those two things are equal to 0. Force of static friction equals or minus Fg sine theta. So I can solve for that. I can say that this is 0 equals force of static friction minus Fg sine theta. And I can then say that force of static friction, okay, is equal to Fg sine theta. Well, what is Fg sine theta? Well, I can determine it. I know the mass. Fg is equal to mg, which is equal to the weight, remember. So I know that that is 22 kilograms times, let's see, did I use 9.8? I did. So I'm going to assume G is equal to 9.8 meters per second squared. Okay. 9.8 meters per second squared times sine of 30 degrees is equal to 107.8 newtons. Okay. So there is B. Okay. Calculate the normal force acting on the box. Well, now, if I want the normal force, It's in my y direction, correct? So let's go over here and look at this. I'm going to sum these forces in the y direction. And it's not accelerating in the y direction because it's sitting there. So forces in the y is equal to mass times acceleration in the y, and this is 0, which is equal to force normal points up minus fg cosine theta, because I subtracted it because it's pointing down. So force normal is equal to fg cosine theta. So you'll plug in the mass, 9.8 times cosine of theta, which theta is 30 degrees, and I will get 186.7 newtons. If you use g as 9.8 meters per second squared, 6.7 newtons. So this is C. What is the coefficient of static friction? Well, by definition, coefficient of static friction is equal to mu S Fn. Now, didn't ask for the maximum. At this moment in time, we're probably in, did it tell me it's slipping? No. I know at this moment in time that I don't know if I'm at max. It didn't tell me I'm slipping, but I'm going to calculate what the effective coefficient of static friction is at this moment in time. So what is it? Well, force of static friction is equal to mu of S times Fn. So mu of S is equal to force of static friction divided by Fn. I found the force of friction earlier at 107.8 newtons. I know force normal because I just solved for it. So I divide the two of them, which I don't have room to show you, but I'm pretty sure you can get that, and I get 0.57. There's D. A customer is pushing a 15-kilogram shopping cart at a constant speed. That's a very important phrase. That means acceleration is 0. That means the forces in that direction, whatever that direction is, which we'll call X probably, at that moment in time, those forces are equal to one another. Towards a shelf of soup cans that are 10 meters away. So I have some distance. We're going to draw a picture, by the way. A shopping cart has no wheels, and the coefficient of friction between the floor is 0.3. So let's draw a picture. I have me pushing my cart. I have no wheels. I have some soup that I'm going to have over here. I have friction because they gave me a coefficient of friction. They did not tell me it was a frictionless surface, right? I know that this is, what else do I know? I know this is 10 meters. It's going to be delta X right there. Okay. I am moving with the velocity of 0.4 meters per second. I know acceleration at that moment is 0. Okay. I have velocity, I have acceleration, I have delta X. I have a feeling we're going to need it. A. Draw a free body diagram while the cart is being pushed at a constant speed. Okay. What this dot represents my cart. I'm pushing the cart, right? Well, let's do the easy one. Force normal because the cart's on the ground. Force of gravity, which is pushing down or pulling downward on it. Those two have to equal each other because I'm not accelerating up in the sky and I'm not going down into the earth. I'm pushing on it. Well, they tell me I'm at a constant speed. I can't have that because that's the only force in the X direction, then I'd be accelerating. So this is a force of friction. What kind of friction? I'm sliding, so it's got to be kinetic friction. Okay. And notice the length of my lines are hopefully close to one another. And that is because acceleration is equal to 0. So those two forces have to equal each other. So there you go. That's A. B. Calculate the kinetic friction force acting on the cart. Well, I know that the force in the X direction is equal to mass times the acceleration in the X direction. I know that that is 0. That is equal to the force of the push minus the force of kinetic friction. I don't know the force of the push. They didn't tell me the force of the push. So I can write that. That doesn't, I mean, that helps me maybe in the future, but at this moment in time, I don't know this value. Okay. So I'm going to have to rely on the definition of force of kinetic friction. Force of kinetic friction is equal to mu sub k times force normal. I can determine the force normal on the cart because I know the mass of the cart. So I'm going to have to find force normal. And they gave me mu k in the problem. 0.3. Okay. So let's find force normal. What direction is in force normal? That's in the y direction. So let's sum the forces in the y direction. Mass times the acceleration in the y. That's a y. That's equal to 0 because I'm not accelerating down into the earth. That's force normal minus Fg. What's mg? I mean, sorry, what is the force of gravity acting on it? That's the mass times the acceleration due to earth. So force normal is equal to Fg, which is equal to mg, and the mass was 15 kilograms, and I'll use 9.8 because that's what my previous work was. And I believe force normal is 147 newtons. Did I have to find that? No, I didn't. Okay. So now go back up here, plug that into force of kinetic friction, which is equal to 0.3 times 147 newtons, which is equal to what? Am I doing this the wrong problem? $44.1. Okay, so this is B. All right, let me pause for a second. Okay, that's B. C. Now, before we get to C, we change the problem. After 5 seconds of pushing toward the shelf at a constant speed, the customer realizes he's going to be late for dinner and begins pushing the cart with a larger force. He reaches the soup an additional 6 seconds later. Okay. So, where was he after 5 seconds? So we're going to have to redraw this picture. So here he is originally. He's pushing this cart. He had a velocity of 0.4 meters per second. He started at time equals 0. Where was he? We know the soup is located at x equals 10 meters. We'll assume that this x is 0 here. We were told that that was a distance of 10 meters. So where was he when he started to change his situation? 5 seconds away. So this is now at t equals 5 seconds. Where was he located? Well, 0.4 meters times 5 seconds gives me, he's at x equals 2. He's at x equals 2. So this is not drawn to scale. Okay. But he's got how many meters left to go? He's got delta x left to go of 8 meters because he still has 8 meters to go. So he reaches the soup can an additional 6 seconds later. 6 seconds from plus 5 seconds, that's at 11 seconds. So the change in time here is 6 seconds. Okay. So what was my velocity at this moment in time? The velocity was 0.4 meters per second. I have three things. I know my initial velocity was equal to 0.4 meters per second. I know that the change in position during this next section was equal to 8 meters. And I know that the elapsed time, or the time that it took to go that distance, was 6 seconds. I know three things. Pretty sure I'm going to need acceleration because I'm dealing with forces. So force equals mass times acceleration. In fact, that is what C asked for. What is that acceleration as he pushes the cart with the new larger force? Because I had to increase my force. This original force of the push, I had to increase, right? Which, by the way, we found force of friction. Isn't that the same as the force of the push? Because those were equal to each other. Anyway, all right. Acceleration equals, well, I can find it using delta x equals v initial times time plus 1/2 at squared. Solve for a. A is equal to delta x minus v initial times time divided by t squared. Multiply all this by 2. Plug in all your values. You'll get acceleration is equal to 0.31 meters per second squared. Notice it comes out to a positive number. That makes sense. I'm accelerating to the right based on our drawing. This is answer C. D, calculate the new force, the new larger pushing force. All right, well, first, before I do that, I want to make sure we have an appropriate free body diagram. Here's my new force. Here's the force of friction pulling to the left. I now have an acceleration to the right. This force of friction, this is kinetic friction. It's constant no matter what. It's independent of the force that I push. And I found that earlier, so I now know that information. So this is in the x direction, mass in the x direction. So sum of the forces in the x direction is equal to mass times acceleration in the x direction is equal to the force of the push minus the force of kinetic friction. Force of the push is equal to the mass in times the acceleration in the x direction plus the force of kinetic friction. The mass is 22 kilograms. Nope, sorry, 15 kilograms times the acceleration that we found and plus the force of friction we found earlier, which is 44.1 newtons. And we find the force of the push has got to be greater than, and it's 48.8 newtons. And that is for D.